Now, to understand what's going on a little bit better, and a couple more properties of vector spaces and transformations that everybody should know. Okay, we get the best fit by getting the x vector, the CBA vector, where A, B, and C are the parameters of the quadratic model of y equals AT squared plus BT plus C, with a property that when we transform that vector, it's as close as possible to the B vector. Now let's go back to our picture here. Okay, where's our B vector? Tell me where in this picture you would expect to find the B vector and why. Think about it. Would it be over here? Would it be over here? Would it be in here? Would it be in here? Would it be out here someplace? Okay. Well, you know, you might have a good answer to that depending on whether you've seen some of these videos, but or been in class and picked the idea up. But the point we want to make is that the B vector is probably not in either of these subspaces. It is over here because the B vector, of course, it's a vector of dimension 5, right? So it's got to be over here in the 5-dimensional space. It's not in this 3-dimensional space that A acts on. It's in the 5-dimensional space that you get when A multiplies a vector x. Okay, here's B. We don't expect B to be here. But this is the column space. This is where all the vectors from over here end up, went under the transformation. So wherever x is, so you know, x is over here someplace. Let's just say this is the, well, wherever the x is over here, it comes, wherever x is over here, AX is over here. Okay, and if this is the AX that's closest to B, then we just have to figure out what x came from over here. And that x will be our CBA vector that'll give us our best possible quadratic fit. Okay. Now, we don't expect B to be in here. There is a property of vector spaces relative to matrices that says that any vector in the whole space is a unique sum of something from the row space and something from the null space. And that sum is unique, so that the unique vector that you would need from the row space of A transpose, in order to add that to the unique vector from the null space and get B, well, that's what AX should be. So, it's a little difficult to understand. It's hard to get your head around it. You've got to keep thinking about it. Okay, AX is the unique vector in the column space of A, which is the row space of A transpose, which when added to a vector in N of A transpose, and that would be a unique vector in N of A transpose, gives us B. The difference, AX minus B, then has to be in the null space. Of A transpose, which means that A transpose times AX minus B has to equal the 0 vector. So A transpose times AX minus A transpose times B equals the 0 vector. So A transpose AX equals A transpose B, and this is the equation that we solve. It gives us 3 equations and 3 unknowns that we can relatively easily solve for A, B, and C. Okay, now that's for the depth versus time data. Well, there's nothing about this that was specific to the fact that this was R3 and this was R5. So everything that we say here applies equally well over here. Okay, the matrix that we get for the distance versus time data is this. And again, we fully expect that this matrix, and we can prove that it does, I mean, it's very easy, we can easily reduce this matrix, just subtract the first row from every other row, well, from the second row, and then, subtract the first row from every other row, normalize this, and subtract this row then from every other row. You get this, 1, 0, 0, 1, and then rows of zeros. So the matrix A reduces to this. Now, this is a little hard to read, hard to write down here, but the row space then has dimension 2, this row and this row. The null space has dimension 0 because this matrix acts on vectors in R2, and the dimension of the row space plus the dimension of the null space has to equal the dimension of the space the matrix acts on. Okay? The matrix reduces to this. Row space has dimension 2, null space has dimension 0. The column space has dimension 2. But this space over here has dimension 5. So the column space here has dimension 2. This space has dimension 5. Your B vector over here is just the vector, I've covered it up, but it's just a vector consisting of these numbers over here. And everything we said applies to this, everything we said in this picture mimics something over here, okay? In other words, this picture represents this situation just as well as it represents this situation, with the only exception being that this thing has dimension 2, this thing has dimension 2. And this space has dimension 2, so this null space has dimension 0. And this space has dimension 5 because, of course, that's what this matrix maps things onto. It's got 5 rows. It maps things into R5. And since this has dimension 2, this is orthogonal to this with dimension 3. 2 and 3 adds up to the dimension of the whole space. But every bit of this, other than the fact that the dimensions are just a little different than these, applies equally well here, which means we can still apply the same equation and find our x vector that in this case gives us the parameters of our linear model, the numbers that we put into our linear model, which I've erased, but the linear model is S equals A plus BP. So we get an A and a B put in here. We get a straight line graph, okay, a linear function that is the best linear function for this data.